Exercise 41.1. This exercise is to be solved manually. Consider the region enclosed by the graphs of y equal to x and y equal to negative of x squared plus 6x minus 4. Part A. Sketch a quality graph of the described region. Provide a graphic approximation of the area of the region. B. Provide a calculus calculation that yields the exact area of the region. C. Assess the correctness of parts A and B by examining for consistency between the two results. So, Part A, graphic approximation. Well, looking here at this function, I want to kind of visualize matters a little bit first so that I plant a coordinate system that will fit all the important region in one step, I hope. So here, visualize, of course, a diagonal line, 45 degrees, going through the origin. Over here, alright, a quadratic function, y equals to ax squared plus bx plus c, one of those. And what do we recall about that? Well, the graph will be a parabola. The axis of symmetry will be vertical. This one, with the negative x squared there, will open down. This will be a translation of y equal to negative x squared. And a little formula might be worth memorizing is that the x-coordinate of the vertex will be at negative b over 2a. Okay, so let's see, maybe a little calculation there. So for the y equal negative x squared plus 6x minus 4, the x coordinate of the vertex equaling negative b over 2a. In this case, that's the negative of 6 over 2 times negative 1. Looks like that's going to be a negative 6 over negative 2, a positive 3. Then the y-coordinate by just substitution. Okay, so there will be a negative of 3 squared, that's a negative 9. 6 by 3, that's plus 18 minus 4. So what are we looking at there? 18 minusing 13, that's at 5. Alright, so I see we're going to have a vertex at 3, 5. It's going to open down. We have this diagonal line. Alright, I think we will do well to create a graph that primarily has the first quadrant in plain sight, and probably not necessary to go more than about 5 units in the positive x and the positive y direction. Okay, let's start working on that. So here we are. I decided to scale this at 1 centimeter equal 1/2 unit, because this way I can get a larger graph, and larger graphs yield more accurate approximations. So, first at bat, that y equal to x graph. How about that? Straight line. Of course it goes through 0, 0. Another point for something accurate, maybe for something far and distant like the point 5, 5 would make a nice second point. So, looking parallel to this existing y-axis right there. And here we go. Going to use a red color for this graph. Try to use different colors for everything. And I'll label this. I want to try to start distinguishing things here, so I'm going to now call this not just y equal to x, so I'll call this y sub 1 equal to x. Alright, now I'll go to another color, blue, for this parabola. Alright, first up, the vertex, the point 3, 5. Okay, let's get that. There. Could even go so far as to put a V for vertex 3, 5. Alright, now I use the idea that I know this is a translation of the y equal to negative x squared graph, which I can pretty much mentally compute. I know for a y equal to negative x squared graph, having the vertex, I would go left 1 down 1, right 1 down 1, and left 2 down 4, right 2 down 4. That takes advantage of knowing this is a translation of that graph to speed things up and give very accurate points to graph. So here we are, left 1, down 1, left 2, down 4, and right 1, down 1, right 2, down 4. Okay, sketching that parabola here, about like so. Label this. Okay, this is now going to be the y sub 2 equal to negative x squared plus 6x minus 4. Alright, now it's evident that the enclosed region is right in here. Want to give that some shading and label that. Alright, so I want to label this now so that anyone looking at my graph can know exactly what's going on. And here we have the enclosed region. Alright, now I want to try to provide a graphic approximation for the area of this enclosed region. Here's where I would try to use a plane geometry figure, which means things like triangles, squares, rectangles, trapezoid, circle, something like this for which I have the formula memorized, and approximate this region by means of using plane geometry regions. Okay, so in this case I might do something like this. I'm looking at this, it looks roughly triangular, so this will be one side of my triangle here, and then I'll come along, say here, about there. I'll get a dashed line going for one side of this triangle. I have some region outside of my triangle. I imagine I use this outside region to fill in the void of my triangle. So here, maybe there. Okay, so just visually, it looks like this could fill in this here, and so this triangle might have the same area as does the region in question. Okay, so I'll make a note of that. I'll say the area of enclosed region is about equal to the area of the dashed triangle, and so that should mean 1/2 base times height, and that means another thing here, by the way. Now I've got this triangle, it's got sides that are all oblique, right? Now I can easily use this because my axes are scaled the same. See, it's 1 centimeter is 1/2 unit in the x direction and the y direction. So that makes the graphic approximation simplest of all when you have that situation. If that's not the case, I would have to be restricting myself to shapes whose important sides are parallel to one of the axes. And we'll see that situation in some later exercise. But for now, I can get away with this triangle with all kinds of sides that are all oblique relative to these axes, and just be fine because they're scaled the same. So what about the base? Okay, that's right along here. Now it looks like about 8.5, we'll say 8.6 centimeters. Now remember, centimeter is only a half unit, so 8.6 centimeters is really 4.3. And the height of this triangle looks like about 4.2 centimeters. So that really means 2.1 in terms of length. And then what's this? You can always do a little basic arithmetic off to the side if you want to. Let's see, what do we get here? 4, 0, 6, 8. We're going to have 3, 9, 2 decimal places. 9.03, half that, about 4.5. 4.5 square units. Okay, there is our graphic approximation here. Now this is the real important conclusive statement of part A, so I want to put this in a very prominent kind of cloud here so that it jumps off the paper, so someone reading this will certainly see what we're really after here. And so therein lies our graphic approximation, part A. Looks like we're ready to go to part B and try out a calculus solution. Alright, calculus calculation. For this, I need to first decide what kind of strategy I'm going to use. I'm calculating the area of a region with calculus. So, like all the geometric applications of calculus, it's a matter of deciding what kind of slices to be using. Doesn't matter whether you're doing area or volume or arc length, calculus always slices it up into little pieces and sums up the pieces. Alright, in this case, since I'm in rectangular coordinates, I sort of have two choices, two strategies that work. One is to use vertical rectangles, thin vertical rectangles. The other choice is a kind of a plan B, and that is to go to horizontal rectangles. Alright, so in my mind, I look back at the region and I imagine slicing it up with vertical rectangles, and I'll do that now. Okay, it looks like the vertical rectangles are working pretty well, and the reason I say that is because the height of the rectangle is always defined by the y sub 2 curve, and the bottom of each rectangle is always defined by the y equals x curve. So that'll make these kind of rectangles very convenient to use. Alright, so I can kind of say here that the area will equal the sum of vertical rectangle areas, and the reason we have this definite integral sign being an elongated S is because it is a summation. So we're going to sum up from A to B. Our areas of these rectangles, I need their height, which in our case is a y sub 2 is the top minus y sub 1 forms the bottom edge, and the thickness of these is along the x-axis, so that'll be a little dx thick. Okay, so there's my starting point for using a definite integral here. Now we have some details to work out. Alright, what about those limits of integration a and b? Where do the widths of those rectangles dx start and end? Alright, as a subcalculation, I'll put an asterisk so that the person reading my work knows to go down, say here, and we'll work out this. So here we have limits of integration A and B. That's what we need to work on here. Alright, well, at those points, it looks like we know we have y sub 1 equals y sub 2, and that means that we've got, well, x is equal to a negative x squared plus 6x minus 4. Okay, I guess we could set this equal to 0. Looks like we have a quadratic equation heading our way. And let's see, this will give us x squared minus 5x plus 4 equals 0. Two numbers whose product is plus 4 and sum to negative 5. Yes, negative 4, negative 1 are such numbers. Got a factorization. Solve each factor equal to 0. X equal to 4. Or x equals to 1. Now, what about this? Again, go back to the graph. Make sure we have consistency at this intermediate stage of the computation. Otherwise, there's something wrong. So we look back at the graph. And what about having x intercepts at 1, 4? Well, looking at the graph, it indeed looks consistent with the graph. So that's encouraging. We feel confident we can proceed forward with this and now have this look like from 1 to 4 of y sub 2 minus y sub 1 dx. Alright, now the next situation is, what about this y sub 2 minus y sub 1? And in fact, we would really like to get an antiderivative here to proceed. Alright, so let's go ahead and go to a second sub-calculation. So 2 asterisks. If the problem's really complicated, I use reference numbers, but when it's not so much, if I think there's just maybe 1, 2, or 3 sub-calculations, I'll use an asterisk, 2 asterisks. Problem that we have at our hands here is this one. We want to know, we're going to work on antiderivatives. So here's an indefinite integral, y sub 2 minus y sub 1 dx. And that means, since x is our variable of integration, y sub 2, well, that's the negative x squared plus 6x minus 4 minus the y1, okay, that was x, gets just a little simpler. Negative x squared plus 5x minus 4. Alright, apparently a chance to use just some power rules here as we go along. So antiderivative here could be a negative 1/3 x to the third power, and then plus, we have an x squared over 2, so 5 halves x squared, and then minus 4x. Since we are recording an indefinite integral, it would be a plus c here. And we want, of course, the simplest of these antiderivatives. So this will be our cap f of x that we use in the processing of this definite integral up here. So now we have this result, negative 1/3 x cubed plus 5 halves x squared minus 4x, evaluated between 1 and 4. Okay, now it looks like it's just pure arithmetic from this point forward. So we got negative 1/3. Going to need 4 cubed. 4 by 4 is 16. By 4 again is 64. Plus, we get 5 halves times 4 squared, 16. And then minus 4 by 4, that's minus 16. Alright, and now we have to subtract the evaluation of this at 1. Negative 1/3 times 1 plus 5 halves times 1 squared is just 5 halves. And then minus 4 times 1, just about like so. Okay, let's see, backing up here, a little simplification, we get 8 there. Okay, and let's see, this 64, no further cancellations there. Looks like we're going to need to go to thirds to get this first number consolidated. So we have negative 64 thirds. And then that's, let's see, here's 40, so give it a 3 over 3 multiplier, that's plus 120, and then 16 is going to need a 3 over 3 multiplication buildup. That makes minus 48. That's over 3. And we're minusing, let's see, the fraction here. Looks like we're going to go to sixths, apparently. And let's see here, we got negative 2 sixths, and then plus needs a 3 over 3, 15 sixths, and then a minus 6 over 6 buildup, 24 over 6. Okay, let's see what happens next. This is, let's see, the negatives, 64 and 48. 112 negatives and 120 positives. Looks like that's a plus 8. That's 8/3. This sixth part here looks like there's negative 26 and then plus 15. Okay, so that would make that, let's see, a negative 11. We're subtracting a negative. We're adding 11 sixths. Looks like we'll need to go to sixth overall here. So this needs a 2 over 2 buildup. And that looks like 16 and 11 more, 27 over 6. Okay, factor 3 does cancel. Now we're looking at 9 over 2. Alright, that's the final number there. Square units. When it's area, I like to just remind myself it's square units, so that when you get to a physical real problem, you're putting your units of measure on there all the time. Alright, and therein lies our calculus solution to this. Now let's start assessing the correctness. Okay, part C, assessing the correctness. Well, let's review here. The graphic approximation was about 4.5 square units. How about that calculus solution? We said it was 9/2, which actually turns to be the very same as 4.5. So the calculation was 9/2, which equals 4.5 square units. Okay, now in this assessment of correctness, I generally try to draw good graphs, and myself, I really like to be within 10% of each other with my graphic approximation and my calculus solution. Then there's that kind of gray area where between 10 and 20%, okay, I believe it's correct, but I'm wishing it was a little better. Maybe I should have graphed better, or maybe there is an error, but I do feel pretty confident in that case. And then if I'm not even within 20% and I've done what I thought was a pretty good graph, that tells me there's an inconsistency and I need to go back and review. Usually the calculus calculation, sometimes it's the graph that has thrown me off. Okay, but in this case here, we happen to have the results happen to actually be equal. So this is kind of almost too good to be true in a sense, but it worked out very nicely. So we can record that fact. These results are, in fact, equal, and thus, of course, consistent. Thus, the solutions to A and B are likely correct. Okay, looks good.